We're reviewing limits for our stuff tomorrow. That's where we're starting today in our review. What were you going to say, Leland?
Oh, I don't know.
Okay, so we've got a visual here. It's going to have one of these guys, like so, because asymptotes happen at x equals 4 and x equals -4, and because they don't cancel, they're still asymptotes and not holes. If they canceled, they'd be holes. That's why you could find a limit, because you can approach a hole. That's Mr. Waffles. It doesn't exist. So these are both asymptotes, and the limit doesn't exist for an asymptote. You could describe it as infinity, but I'm assuming that wasn't a choice. It was multiple choice, or was it fill in the blank? Okay, so what it looks like on the graph, and I don't know I have finance up there. Do I have it in there right? I'm sorry, I just graphed some sign stuff, so my graph is weird. Okay, so Windows 6. Nope. Zoom 6. So just to prove the visual description we had before, it goes whip, whip. We have two asymptotes for -4. And they go in opposite directions, so it definitely doesn't exist at -4 because one's going up and one's going down. They don't approach the same thing. So quick pre-calculus review, which is asymptotes come from the denominator. If they don't cancel, then they're asymptotes for real. And if they did cancel, they'd be holes. You could find the limit of a hole, but not an asymptote. There you go. So rationalizing comes with if you had the square root on the top over something that I don't know what would actually work because I made this up. And this would be, you'd multiply by x plus 1 minus 1 over the square root of x plus 1 minus 1. So this would be the conjugate. Remember that? Okay. And then if you had plugged in, you tried to substitute in the beginning and it didn't work, but this one went to 0 and this one went to 0, which is not the case here because the top didn't go to 0. The top went to 1. So if it goes to 0, then what can you do? If the limit is it went to the top of the top goes to 0 over the limit of x approaches -4 from the bottom goes to 0, then you L'Hopital it. There we go. And you'd say the limit of the top's derivative over the limit of the bottom derivative. And then you can substitute in. Unless you got 0, 0, and then you do it again, and then you plug it in. But it only works if you have 0 on the top and the 0. It has to be indeterminate form, which is this. So that was your chapter on limits in a minute. But asymptote rules from pre-calculus. Now we're like, oh yeah. So I'd have to see the problem. But if you take the test again and get the same problem, do you get the same problems? Or sometimes you do on the unit test and sometimes you don't. Like there's a smaller quantity of questions. So I'll see if I have a chance to play with it and find one and I can post it. What? What do you mean? Indeterminate. Yeah, that's what we call that. You don't have to write that. You don't have to write L'Hopital's rule. It doesn't hurt. I mean, you're explaining what's happening by showing the math. And see how I wrote it separately? Because I was trying to avoid that thing where if you write 0 over 0, they just go, oops, I didn't even write that. 0 over 0, then they just go, no points for you. So don't write this. You can say the top goes to 0 and the bottom goes to 0. Completely separate. Notice I use arrows. Like I'm trying my best to avoid this notation and still say that. Somebody got really particular at some point. Again, beyond my pay grade. Now we've switched directions. Now we're in 6.2. We're looking at 14c. We were given y equals x squared, this, and we're trying to rotate about y equals 8. So if you just took an axle at y equals 8 and rotated something that was too wide, it would be a big round disc that's too thick and has a radius of 8. So if it was solid, it would be from 0 to 2 of pi r squared, where radius is 8. And obviously it's too wide. We could actually figure out that volume without integrals. We could do a can, a very squished, flat can, if you will. So that's the solid version. Now we need to cut out the inside. We have to carve it out. So we need to take this inside portion out, and the tricky part is, how do you get it? Now, normally the function x squared represents this part that's colored in. So from the function to here. And we need the opposite. So how do you do opposite? You have to say this whole distance, but subtract this out. So if you had 8, but you subtract out this function, you've subtracted out all of it except for this one little dot at the end, at the very beginning. So it's 8 minus the function is here, and then it's a little bit smaller here because we're at a different x. So it's 8 minus less because our x has moved the y up. If that makes sense. We're at this x, so we're up here, we're subtracting less, and we keep carving it out. I don't know if you, I guess I like craft stuff, so I watch them with the cool machines where you put the piece of wood in and it does carve it out and my brother just got a machine, so he tells me all these cool things he does with it. But anyway, I can imagine it carving it out. This is carving out a big chunk, and as it moves to 2, deeper and deeper, it's following this graph, if you will. So we're subtracting, we're carving out, but we're starting with 8, and we're subtracting y squared, and that is this, except is it really y squared? It has to be x squared. Sorry. Everything has to be an x. dx. So we would, if we were making this whole thing, like erasing the entire disk we had, we would subtract 8. So subtract 8. But as we move down to a different x value, a different depth, so we're carving this way, we subtract whatever this function tells us to. So now we're subtracting a little bit less, a little bit less, a little bit less, and that becomes the radius. And then we integrate it. And there's a pi here, pi r squared, pi r squared. Does that help explain it better? So 2 is the depth of it. And I mean, you could make your whole bowl deeper if you made it 4 here. Then that would be here. That'd be what, so you're adding up, this is a hollow, it just has this depth. And then your next circle is a little bit deeper here and here. And then you've got more for the next circle and more here. And by the end, you carve out little more pieces. This is straight, right? This is this. Okay, this is a terrible picture. In my mind, it was going to be great. So each time you go from at 0, you carve out this big piece. That's 8 minus just a little bit, because your x right here is like 0.1. And then you carve out a little bit less because your x value's gotten bigger. So the whole is what you carve. It's smaller and smaller and smaller, because as you subtract x squared gets bigger and bigger and bigger. And so you're carving out less. I don't know if that makes it better. is a little iffy. And I believe there's probably Khan Academy on this as well. And there's some videos that I didn't make you watch. But that would be a great thing for you to go back to during spring break. And I don't have like a whole slew of assignments for you, but you may want to spend 30 minutes and do a unit test in something, or watch a video. You can watch any of the videos on AP Classroom without me assigning it. I assign them because I want everybody to be on the same page on certain days, but you can go watch somebody else explain this and see what examples they use, if they say it in a way or draw a better picture than I have. I haven't really shown you, except if you looked in your own book, some really good pictures, which I told you I would, and I'll try to find them and share them with you in class, because the the better the pictures are, the more you can imagine how that works. But I would say this is the hardest kind of problem. Not rotating it on an axis. This is not the boundary of your function, which is why we're having to do this subtraction. Whereas the other ones where we made like a bead, if we rotated it, if the function looks like this, then this is one of the boundaries of it. It changes kind of how you subtract things. You can't see that. There you go. I'm not going to make up a problem because that would be awful. The best I can say for these is to keep practicing and do your very best in FRQ to set it up. So at least at the minimum, if you know that it's perpendicular to X because you're rotating it this way, so perpendicular to X, if you put everything in X, that's a start, like you're on the right path. And that's kind of where we are. This is still pretty new for us, so that would be a great start to it. But we have lots of time to pull out more problems and do them a little bit at a time. I have a whole review that has all kind of great problems to do, which includes these later. So we still have a little bit of time left in class, and the students are going to work on their own Khan Academy review by looking at some unit stuff. Reminder, the exam tomorrow is starting at 9, so be here before 9. We're starting the hour session at 9 o'clock. So coming later will mean a shorter time in that section. You do need your calculator, so charge her up and bring it. And we'll be here till approximately 12:30. Although when you're finished with the second set of FRQs, then you're not required to stay for the whole hour. You could leave when you're done. All right, we'll see everybody tomorrow.